Do I understand correctly that there is no analog of small disk operates which would reflect, which will explain the bialgebra structure in homology?
This is what I was asking you guys here. Yeah, okay, so yeah, so the choice of remarks here is kind of, this is the first time I've talked about this really, and I made some choice, but for the n-to-1 operations, this remark about the dis and the BV operand and why God knows is like it's like there's a complete you feel like you have a complete understanding of what's going on, but when you start including these co-operations, then you can see this Lie bialgebra structure, but are there more operations there derived below, and are there more identities? And you can label all of the operations by this combinatorics of naive string operations, but one has to sort of study that, and I don't know what the universal structure is. I asked you about the what?
Maybe postpone discussion. Can we have discussion?
Yeah, right.
I have just one remark that this those two things works when we have not just manifold, but at each point we have positive direction, going in the positive direction.
Yeah, no, that's another. Yeah, you could. That's what I say. You can put in auxiliary geometric conditions, like make all your strings go in a cone of positive directions, and all the operations respect that. So you can actually, I think it will fit with Eliashberg's talk. And then the contact structure, you go transverse to the contact, and the interaction in the symplectic manifold should be positive. But you could formulate something that will make this discussion somehow be compatible with that discussion. I don't know the relationship, but it'll somehow be, you can make it compatible with side geometric consideration.
You make 5-minute breaks and have discussion.
Wait, our discussion is supposed to be this afternoon.
No, right now. Continuation of 3 talk. 5 minutes.
Oh, we do it now? Okay. We forget the one this afternoon.
No, separate. Another afternoon.
Your discussion afternoon. Whatever question.
Oh, I see. Okay, I understand. Okay, the morning discussion. The morning discussion. I'm sorry.
Before afternoon discussion.
No, I'm sorry.
That's cool, yeah, actually. Fantastic. I want to feel it. Yeah.
Yeah. No. Right.
Now we discuss, yeah?
I have a question to consider.
So go to the microphone.
So the question could have personal consequences for my own career. The question could have personal consequences for my own career, so that's why I wanted to discuss this. So if I understand correctly, the problem of singularities in both physics and mathematics has been solved. If that is so,
No. It was not said. It was never said.
But I don't understand then exactly what the statement means.
Ask an innocent question.
Okay.
Not so aggressive. Come on. Just
Okay.
ask an innocent question.
An innocent question.
A scientific question. Not defending your position in the field or your field.
No. Scientific questions. Okay. So the scientific question has to do with definition of everything that is not single. Everything that, if I understand correctly, the problem singularities in mathematics and physics at a certain level, which I don't understand, so he will answer, has been solved, and the only problems remain. Wait, he will answer. No, wait, I don't understand. So let me finish my question, and then you'll answer. So then he went on and said, you went on and said that there are still problems in chemistry and biology, and therefore.
You don't have a question, sir. You don't have a serious question.
Okay, but then I still want to understand what does it mean that the problem of singularities or compactification has been solved.
No, wait. Let me say.
But I misunderstood it as an analyst. I'm sorry.
He said. I think he said that the point of view.
You go to microphone.
Yeah, I think he said that the point of view of looking at directly at the naive set defined by the equations and taking its singularities is not a good point of view necessarily. There are other points of view where you sort of write the equations that express the singularity and manipulate them in an algebraic way and impose a geometric view on this algebraic structure. And then, somehow the singularity is kind of hidden somehow. So it's a point of view.
I understood very well at the level of algebraic geometry. That's why I'm asking the question. In what sense? Yeah, so this is much more. This is at the level of physics. So I would like to understand at that level what it means. So I'm sorry, I may be very naive, but I want to understand what does it mean in terms of physics, not in terms of algebraic geometry. What you describe is algebraic geometry. That I understand, and I think it's a wonderful idea. But I'm just saying, in terms of physics, what does it mean?
Any of us understand what the idea is. The assertion is that he made it. There is an idea. I don't think we understand what it is.
Okay, but that's what I'm asking.
No, what are you asking?
I'm asking what does
No.
physics.
And no, in physics, if you have something not solved, no. It's not solved. It's kind of, it's not formulated. No, there was still one of great Hilbert problems not yet resolved. Something I thought it's 6 or 9 Hilbert problems give mathematical foundation of physics. It's not. yeah. So we don't understand what we're talking about. But as I understand, talking with people, that if there's something you can't really describe by good functions, at least in simple systems like quantum field theories, I have to say, with some concentration of more and more things in one place, then it will be new theories at the end which describe things. So the whole picture that physical theories form kind of strata, smooth manifolds, and all things is manifold with corners. So there is conformal field theory, quantum field theory, string theory, and M theory. All things attached to each other. And
So you mean at the level of theories?
theories, yeah.
So the categorical level?
Yes.
That's what it means? Okay,
Yes.
So I guess you answered my question. So it's purely a meta, it's
Meta.
formal
It's not
meta
a,
that has to do with the definition of quantum field theory.
yeah.
And how they see relative to each other. Is that what you mean?
Yeah, if you have concentration of effects and more that we cannot describe by old means, that will be some new series.
Yeah, I have a question to Bob, and so I think I thought for many years without any success, but let me formulate the question maybe and see the reactions of the thing. Try to use this strange thing. I don't know if that's to work or not. Work fine. So, as was formulated already today by Maxime, we have some kind of parallelism or duality between singular and open manifolds. So, if we have a compact smooth manifold, then we have Hodge classes are exactly in the middle. If X is open, so compact, smooth. If X is only compact, but not necessarily smooth, then we have inequality in one direction, and it is smooth, but not necessarily compact, then we have inequality in another direction. Now, one can try, so the perverse cohomology is a way to reproduce purity for compact manifolds which are not smooth. In very naive way, in which I don't think we can work, it will be the following. You take all possible resolutions of X, you take cohomology of all possible resolutions, and you take a common part. And common part would be an intersection cohomology. Now, if this approach is correct in some way, then one can try to repeat the same approach for, say, smooth non-compact. You take all smooth compactification, you take cohomology, and you try to take the common part, which will be, so it's a perverse cohomology of non-compact manifolds. Now, in the kind of trace formula which Bob was discussing, the original manifold was smooth and non-compact. And compactification was invented, so to make sense of computations. So my question is whether you think that there could be some theory which intrinsically intersectional homology on smooth manifolds, which at least in terms of definitions will not require a choice of a particular compactification.
Well, I also thought about this often in fail.
Okay.
I think comment about this.
So I know one way in which such a symmetry between smoothness and compactness can be made precise, which is in terms of this formalism of four functors which I was working on in the last year. And when you look from this point of view, it's clear that the symmetry is not perfect. There is one particular place where it breaks. And what actually happens is that there is a symmetry between compact and, I should say, a tau, or smooth dimension 0. And we don't really, smooth doesn't have a proper companion. So let me try to say it in terms of what is further from what and what is closer to what. In some sense, it looks like compact things are much closer to non-compact things than, no, it doesn't work this way. Let's see. So in a completely symmetrical world, there would be a lot of other objects. So the spaces would embed into something much bigger, or spaces topological or algebraic varieties, doesn't matter at all. Something much, much bigger, which basically should have something like two different dimensions. Let's call it D usual and D unusual. And usual topological spaces are exactly the spaces of unusual dimension equal to 0. D unusual equals to 0. And in this world, there would be a total symmetry between smoothness and compactness. But when you go to this class, basically there will be a lot of gadgets which are non-compact. No, it's not a way. This is where I'm making a mistake. There will be a lot of gadgets which are compact, but of higher unusual dimension, which will be somewhat analogous to things which are smooth but not at all.
Can you give an example of something with dimension 0 1?
No. So these things should be somehow intrinsically, locally non-separated. This should be objects which are very non-separated in each point. It's something like the case when the diagonal is an open embedding, or maybe, but I don't know this part of mathematics. I don't know how to make an example. But
do the two D's relate to your two notions of suspension?
No, doesn't seem to be so. No. No. No.
You said something.
Why are you talking about the second dimension? Maybe this is more unusual dimension. Maybe that's still more unusual.
No. This is something very, very precise. So if I have a theory which assigns to any space a category and to any map of spaces 4 functors, like lower star, upper star, lower shriek, and upper shriek. And plus there is some small additional structure. I don't want to write it down explicitly. It's very explicit. Then to any given a theory which starts from a category, I don't care what it is. That's an analog of a category of spaces, and takes values say in the 2 category of categories. So to a space assigns a category, to a map of spaces assigns 4 functors, and to a Cartesian square it assigns some additional structure. Then to any such gadget defines certain classes of maps on this category. The behavior of these functors defines certain classes of maps. And each such structure, in fact, defines naturally 4 classes of maps. Now, well, somewhat more, but so these 4 classes maybe I should make it 6. The 6. So there's these 2 and this class are the morphisms which are simultaneously belong to both of these. So in the case of, say, algebraic varieties, these 4 classes look as follows. Here I'll have smooth, well, in fact, somewhat more than smooth, but I want to leave this not explained. Here I'll have unramified. Correspondingly, here I'll have a tau. Here I will have proper. Here I'll have separated. And here I'll again have proper.
How could the intersection of 2 identical things are somewhat unique? You said the middle row is the intersection of the top and the bottom.
No, the lowest row is the intersection of the top and the bottom. So the fact that this class happens to completely lie in this class is as if we had, sorry, it's the other way around. The fact that this inclusion holds, it's as if all smooth morphisms were a tau, all smooth morphisms were unramified. So if the axiomatics of this thing has Z2 times Z2 symmetry, absolute complete Z2 times Z2 symmetry, which exchanges rows and columns. So it's completely symmetrical.
In particular, homomorphic image and lost some structure. You've taken a homomorphic image and lost some structure. You've taken your constructions are applied to these mappings, right? You lose information, so they don't have to reflect everything.
No, it's not. The problem is not in this arrow. If I sort of take the universal arrow satisfying some reasonable axioms, it will do the same thing. It is the problem with this category.
So properties, this is a little bit big property because this evaluative criterion of separating the properties are 2, the existence and forever. But in properties, people artificially add separatedness. If you remove it, then
you cannot. It doesn't work. So the sum axiom falls apart here. So just taking something like 2 projective lines glued together in a complement to 1 point doesn't work. So there is something else. There is a huge gap. The gap is the same as between smooth and the tau, and there the gap is the dimension. So the only difference between smooth and the tau is the dimension, and here this dimension is missing. Okay.
The other D.
Yes, this should be the direction of the other D. I would love to see an example, but this axiomatics is indeed 100% symmetrical.
And explicitly you have it with some.
No, I don't have any. I don't have any example of such a two theory, as I call it, which would be completely symmetrical on in either.
Maybe it's with stacks, dimensions of stabilizers.
I don't know. Maybe I should. Sorry, I just had one simple thing. What might be true, in some sense, this second dimension shouldn't add up in products. Should not add up in products. However strange. It should not be additive. It should not be additive with respect to products.
So it's additive with respect to something else? I mean, if it's symmetric.
I don't know.
Somebody else want to say something? Go ask a question.
You mentioned that you can handle PDEs too. You have an example. It's a simple synthetic point of view.
Consider algebraic geometry is PDE point conclusion. Basically, I don't know. Maybe it's not those.
No, but yes, the philosophy can be applied to PDE considerably the idea of solutions.
Yes?
Really changed.
Yes.
This is the new view potentially. Yes, yeah. Actually, it's quite possibly what he said can be a completely view on your mathematics also. You forget about a solution, you have different conceptual solution, and then you don't have singularities. But it's really a radical, very radical change.
Well, that's what I thought you wanted to say. That I thought it was an interesting discussion. The has scientific answer. You agree now? So yeah, this is the right question, and that's exactly the one I wanted to ask. So that's what I thought he understood. He understood exactly what you say. That somehow the problem of singularities is solved if you look from a.
It's a new approach.
It's a new approach.
So the different configuration space of solution.
Yeah, but it's kind of, if I have to take it seriously, this point of view, then basically what I'm doing is chemistry now, because in physics and in mathematics, the problem has been solved. So it's kind of chemistry. So it's a way of choice of words, which I think it's very important. And so that's what I reacted. Anyway, but this was just a friendly discussion. I didn't mean at all to be aggressive. So I should, as an answer to what you say, the fact is that at the quantum level, everybody believes somehow that the problem of singularities will be solved. But there is a huge difference of scales between where the problem will be solved at, I don't know, Planck, something, as far as Planck length is concerned, is something of 10 to the minus 33, and where the problem actually occurs, like in turbulence or like in general relativity. The black holes form at the macroscopic level way before quantum mechanics will play any role. So there are serious issues which really happen in
But I think it's a very good point. So the PDE is kind of chemistry. You may look for physics, you may not like it. There is physics behind chemistry.
Okay, well, so you agree. So finally, you agree that that's what he meant. So
No. I think it's possible to
I will.
chemistry.
Okay, I'll try to give my answer tomorrow. Maybe I shouldn't take any more time, but I'll try to give some answer.
Give it now.
I think it takes some time. Why? What does that mean? You don't need yeah. Well, mathematics has developed. I mean, first of all, I really want to make a point for tolerance in mathematics. I mean, I think visions are very important, but there should be plurality of visions. For the simple reason that in the end we don't know. Even if we are interested simply in the physical world, we don't know what the answers will be. And many times in physics, things have happened unexpectedly. There were developments which had to do, so there are certain developments that had to do with what theoretical physicists want, which is to find, let's say, find a final theory. But there are other developments that have to do with consequences of a theory. And again, I said that before, Euclidean geometry had the axioms established 2,000 years ago, and yet Euclidean geometry continued to develop, and developed to the point, like introducing algebra, and let's say there were certain major developments, like introducing analytic geometry, and then later on Riemannian geometry and non-Euclidean geometry, which finally had an enormous impact in physics itself. So somehow don't put down and don't consider, as you very often do, that things that have to do with consequences of a theory are outside mathematics. Because very often it's exactly these consequences that will have huge impact. And you never know where things are going to come from. I mean, I'll give you another example, Lagrangian theory. This was developed by Lagrange, so let's say Euler, starting with Euler, but it was developed by Lagrange. Just simply trying to understand the consequences of Newtonian theory. It led to something completely new, and now everybody is using Lagrange. I mean, physicists always write down a Lagrange. So it became a principle. So what I'm trying to say is that the consequences of theories, even incomplete ones, like certainly Newtonian mechanics is definitely an incomplete one, but the consequences can be profound. And the same thing with general relativity. We had general relativity today. I don't think we need to go to quantum gravity yet. I mean, I have nothing against people doing that, certainly, but there are also consequences of classical general relativity. By the way, general relativity has an enormous range of applications as it is today, and the consequences can be profound. The consequences of just classical general relativity. So it's not a question of chemistry. Deriving the consequences of physical theories, even the incomplete ones, is part of mathematics. That's the way I think.
Chemistry also a fantastic consequence of the algebra.
But if you are calling chemistry something which is outside mathematics.
Mind of chemistry.
Okay, so that calls for another discussion. So you say chemistry is also part of mathematics. Okay, but then it becomes a little vague. I mean, all these things become why should you make any difference? Why should we call something?
Different level of purity, different levels of purity, they are different. Yeah. Myself, I'm working on the one chemistry.
But purity is in the eye of the beholder. We don't know what is the ultimate. So it may happen that deriving the consequences of general relativity would lead to totally different point of view than the one people have today. I mean, for example, I strongly believe that forgetting about Lorentzian structure is wrong, and it will lead to all sorts of problems for the development of quantum gravity. I don't believe in any. I mean, I believe that some sort of the modern developments are fantastic and fascinating, but I don't think they are complete. And sort of a lot of people claim that we are very close to a situation that everything in physics will be understood with the quantum theory. I don't believe in that. Right.
We need more radical statements. That's probably the stop.